Good afternoon. The topic of my report is NMR investigations of atomic mobility in sodium embedded in porous glass with a pore size 3.5 nanometers. Firstly, I'd like to introduce the plan of the report. Firstly, I'll tell a few words about present results on investigation of different atomic composites, and then we will turn to properties of sodium, basically its NMR spectra, and then we will turn to investigation of atomic mobility and dynamic effects. The topic of investigation of small metallic property, small metallic particles is quite complicated because some metals are very chemically active, so it's very difficult to keep them in stable state to prevent interaction of these particles with air. And another point, we couldn't observe signals of separated particles because the intensity of NMR signals are quite weak, and if we use two-dimensional samples, for example, small metallic droplets on surface of some media, we would have a very small amount of the sample under investigation. In such a case, the good idea appears to use three-dimensional matrices which contain separated small metallic particles, and as these matrices are usually used porous silica matrices, for example, synthetic opals and porous glasses. The size of metallic particles embedded into synthetic opals is about 40 to 90 nanometers. It actually depends on size of silica globes. And as for porous glasses, the size of particles under investigations varies from about 3 or 5 nanometers to several hundred nanometers. Another important point I should mention is that not all the kinds of porous matrices are suitable for investigations of metals, because we should introduce the metal and investigation into porous media. In such a case, the porous media should be not very soft because of surface tension, because we should use a very high pressure in order to introduce the metal into pores. That's why lots of kinds of porous matrices are not suitable, and that's why the most usable matrices are porous silica matrices. As for present results of investigation of non-confined metals, I should mention that mostly investigated are tin, mercury, gallium, and so on. The common property of these materials is a low melting point. That happens because we should introduce a liquid metal into porous glasses, which have not very high melting temperature. So the melting temperature of materials should be less than melting point of this metal, of these silica matrices. The present results show that there is a dependence of night shift on pore size. For example, these results obtained for gallium. At some cases, there was observed dependence of line position on strength of the magnetic field. And for metals in nuclei with a spin equal to 3/2, there is a strong impact of non-confinement on atomic spinlet's relaxation times. Here you can see comparison of magnetization recovery curves for bulk or non-confined materials. This dependence on nano-confinement was explained by existence of quadruple relaxation mechanism, and it was proved by experiments with, it also was proved by experiments with liquid mercury, where were no dependence of were no strong impact of nano-confinement on magnetization recovery. And now let's turn to NMR spectra of sodium embedded into different porous matrices. On this plot, you can see NMR spectra of bulk sodium marked with the green line, sodium embedded into a pole matrix, blue line, red line is corresponding to sodium embedded into porous glass with pore size 25 nanometers, and black one is corresponding to porous glass with pore size 3.5 nanometers. You can see here the left line, which is corresponding to metallic sodium, which will be discussed a bit later. And the right one is corresponding to evidently some kind of oxidated sodium. But in some works, the authors believe that this line appears because of interaction of metallic sodium with silicon matrix. Another point which should be mentioned that actually there is one possible proof of this hypothesis, which is expressed by the following experiment. The sample of sodium embedded into a porous glass was measured once and 60 months later. It's the results of these two measurements are presented here. The ratio of intensities isn't is fitted because we couldn't perform two measurements after 6 months at exactly the same state. So we couldn't trust the ratio of intensities. But yet, the bold line is corresponding to the later measurement. So here we see that intensity of metallic of the line corresponding to metallic sodium has decreased. That happened because the sodium was kept in oil, and organic oil actually contains some amount of oxygen, and it could very slowly interact with the sodium, and it was oxidated. But as for sodium with chemical shift about 0, we can see that the position of line has shifted toward the low frequency range, exactly where the line corresponding to sodium oxide of bulk sodium is observed. That effect could be explained by evolution of sodium, which was previously interacting with silicon or the matrix or oxygen or the matrix, and it was oxidated. And now let's turn to the left line, which is the most interesting for us. As corresponding to the experiments with another liquid metals, the dependence of night shift on pore size was observed, and on this plane you can see dependence of position of the center of NMR line on inverted size of the pores. Another interesting point is the difference of positions of sensors of the lines corresponding to sodium embedded into porous glass, 3.5 nanometers. And there is a slight difference in positions between two spectrometers. A spectrometer with a magnetic field 17 Tesla and 9 Tesla. At this plot, you can see comparison of two NMR lines measured at room temperature. And here you can see that the positions of two lines really differ. That's not an experimental mistake. As it was mentioned in the previous report of Professor Charner, this effect is evidently explained by the presence of dynamic frequency shift. In order to investigate the atomic mobility of sodium, the following approximation was used. It's known that magnetization recovery of 4 nuclei with spin equal to 3/2 could be expressed by the following formula. The previous experiments with relaxation recovery were usually performed for gallium, and nuclei of gallium are more convenient for such an investigation because there are two isotopes having different quadrupole constants, and so it is possible to perform one measurement at one spectrometer, and we obtain the same correlation time, the same magnetic contribution to the relaxation, but actually relaxation times relate as gyromagnetic ratio, but yet it's possible to fit at the same time the two relaxation curves. But in case of sodium, we have only one isotope. So the solution was to perform measurements at two magnetic fields, and we have two different values of resonance frequency. So we can simultaneously fit two relaxation curves. And the rest problem is to determine magnetic contribution to the relaxation time. In general, the first possible approach is to believe that there is no strong dependence of this relaxation time on confinement. But yet, there is more exact solution which could be used in order to determine this value. Let's perform temperature measurements at low temperatures and take into account dependence of inverted T1. When the atomic mobility slows down at low temperatures, this contribution to the magnetization recovery is almost absent. And the proof of this effect you can see here. There is no dependence on magnetic field at low temperatures. At high temperatures, the difference is explained by different contribution of quadrupole mechanism. At low temperatures, the relaxation time doesn't depend on intensity of the magnetic field. And so here we can see that the magnetic contribution is inversely proportional to temperature. In such a way, we could predict the value of this contribution at any temperature. And finally, we have obtained the values of correlation time for every temperature. And on this plot, you could see fitting curves, which were obtained using calculated values of quadrupole constant and correlation times. At this plot, you could see dependence of correlation time on temperature, and using Arrhenius plot, we could obtain another important value is activation energy of such atomic motion. Actually, this value is quite close to activation energy in liquid bulk sodium. And that means that it's less than activation energy of bulk solid sodium. Thus, we could conclude that atomic mobility in sodium could accelerate when we investigate non-confined particles. And another point which is connected to dynamic shift of resonance frequency is we know the temperature dependence of correlation time. In such a case, we could evaluate such a value as Larmor frequency multiplied by correlation time. At low temperature, it's higher to 1. Physical meaning of this case is we observe different nuclei having each one in different states. Another body condition is Larmor frequency multiplied by correlation time is much less than 1. It's a case when during the measurement we observe all the nuclei averaged over different states, and the most interesting case when correlation time multiplied by Larmor frequency is an order of unity. So in such a case, we observe the dynamic shift. The existence of dynamic shift was predicted and observed in SR spectra at the 17th. And in case of nuclei having spin equal to 3 halves, we have each line consisting of 2 components, and position of these 2 components depends on ratio of Larmor frequency multiplied by correlation time. In case of fast atomic motion, we have similar positions of 2 lines. In other case, when we have slow atomic motion, we have 1 broadened line, and the second is observed. And using exact expressions for width of these 2 lines, using exact solutions of positions of 2 lines, we could calculate exact line shape of a signal of sodium for different magnetic fields. Actually, in order to do so, we should solve one more technical problem. It is to determine different contributions to the line width, because there is not only contribution from dynamic effects, but for example, a contribution from a non-ideal distribution of pore sizes. This distribution was calculated using information about pore size distribution and having information about dependence of night shift or pore size, and this contribution is expressed by black line. When using sequential convolution of functions, we introduced field-independent broadening of line, and finally we obtain again we used convolution of these functions. We obtained the final NMR line, and here you can see comparison of calculated lines with experimentally observed for 2 magnetic fields. Well, thank you for your attention.
Thank you. Please, questions today? Excuse me, the last slide, please. I have missed, what is it, frequency in parts familiar? Relatively, what?
All the positions of lines are measured here relative to solid sodium chloride. Actually, this point was used in order to observe small line shifts, because we could have, due to some reasons, a slight drift of magnetic field. So we used a reference.
Questions?
the nitrate because it's very feed up.
No, thank you.
Makes no sense.
Again.